Welcome back to the Marine Hydrodynamics course. So in our last class, we talked about the different vortex structures and their properties. And today we'll be looking at the vorticity equation. So the equation which I have here, and you must have recognized, is the Navier-Stokes equation in vector form. So this is the Navier-Stokes equation. And what we are going to do to derive the vorticity equation is just that we are going to take the curl of the Navier-Stokes. So we are going to simply take the curl of the Navier-Stokes equation. And why do we do that? Because we know that the curl of velocity gives us vorticity, and we do have a lot of velocity terms here, so why not just take curl of the Navier-Stokes equation and see what result we get. So after we take curl of the Navier-Stokes equation, we get something like this. So this is the curl of the Navier-Stokes equation, and after this is just a few mathematical manipulations which we do using mathematical vector identities, which you can look it up, and the final equation which we get is this. So this is the final vorticity equation here, and here of course omega equals to the curl of velocity. So this is the final vorticity equation which we have got. And of course from this equation you can just look at the equation and think about certain scenarios and see if the equation is valid and if it satisfies certain rules. So if you remember, in our previous lecture we had talked about that if a flow is irrotational, it is irrotational always. So once irrotational means always irrotational. So as you can see here, if I put if the flow is irrotational as of now, then I'll put omega as 0, and as soon as I put omega as 0, I'll get d, the material derivative of vorticity, as 0. So this means that once irrotational, it will always remain irrotational. So this is one thing to talk about. Similarly, if the viscous force is 0, you can simply put 0 here, so that will give you d omega by dt equals to omega dot the del into velocity vector, right? So here in this case, viscosity, you can think of it as a diffusivity of viscosity and momentum. For example, you must have seen some photographs, or let me just copy an image here. So as you can see this image, okay, let me just resize it quickly. Yeah. So as you can see in this image, at the boundaries, the flow is kind of sticky, and as it goes away from the boundary, it becomes a little more slippery. So that's because of viscosity. So if we include viscosity, of course, if you remember, we'll have the no slip condition and etc. Because of viscosity, and therefore the velocity here might be slow, and as it comes towards the center, the velocity of the particle becomes really high. So that is something which happens due to viscosity, and it's kind of, you can think of it as the diffusivity of vorticity. So moving on, let's talk about another really important phenomena. So for that, let me go to a fresh page. So let me quickly go to a fresh page, and let's talk about what potential flow is. Okay, so this is something interesting. Now, how can a flow how can a flow be called a potential flow? Because we have seen the word potential with maybe energy and forces, etc. But what is a potential flow? So generally we define a potential flow as an ideal flow, flow plus there's an extra condition that it should be irrotational. So in its heart, potential flow is defined as an inviscid flow, which is viscosity is 0, inviscid flow. It is an incompressible flow, and it is an irrotational flow. So these are the three conditions for a potential flow. And we'll see why the word potential comes from, or where, how can we think that it's a potential flow. So the potential flow, what does it say? That if the fluid is irrotational, which means that the curl of velocity is equal to 0, from this we can say that velocity is, it's a gradient of some scalar potential function. So here phi is a scalar potential function, velocity potential, let's say, and the gradient of, we of course know that the gradient of any potential will give you that actual quantity. For example, we can have energy here, so the gradient of potential energy will give you the force or etc. So in a similar way, phi is the velocity potential, and when we take gradient of the velocity potential, we get the velocity. And of course, if we take this, we know that the curl of gradient of anything would be actually zero. So this of course simplifies things. That will always give us a rotational flow. So this is something to talk about. And you can think of potential flow as it describes the velocity field as the gradient of a scalar function. So it's this is just a scalar function. As soon as you take its gradient, it'll define the velocity field of the respective fluid which you are calculating. And in a similar way, suppose I have this diagram over here, and what I can say is from this diagram that this is the potential function which I have, and this is the distance of x. Now the gradient of phi, you can think of it as the slope, of course, because gradient nothing means but it means slope. So as you can see here, as I'm going up this slope, the velocity increases, then it decreases and reaches 0 at this point, and then in a similar way it increases in some other direction downward. So this is what the velocity potential, once you get, you can then figure out what the velocity is, and then flow. So now since we have defined the velocity potential, we need to of course solve it mathematically. So let's see if it is solvable mathematically and we have a closure. So the number of unknowns which we have here is phi, and by continuity equation we know that the divergence of velocity must be equal to 0. So I'll just put your del phi, and this means that the Laplacian of the velocity potential must be equal to 0. So I have one equation here and I have one unknown. So this is a closure. I can simply solve it using the knowledge of differential equation which I have. So now we'll talk about what Bernoulli's equation for potential flow is. Do not confuse this with the Bernoulli equation which we found out earlier, although it is quite similar, but still. So we'll now talk about what Bernoulli's equation for potential flow. So let's see what we can do about this. Let's say we have the Euler's equation which we have seen way before. Let me do that in yellow. Okay, so here we have the del v by del t plus gradient of velocity square by 2 minus v cross omega. So this I'm writing it in terms of vorticity as well. Minus gradient of pressure by rho plus gy. Alright, so this is what I have, and then I can simply substitute the velocity to be the gradient of the potential function over here. And after substituting and doing certain mathematical manipulations, what I am going to get is something like this. So this is what I'm going to get. Oops, let me do that once again. Okay, so this is what I'm going to get. So this is the so pressure equals to minus rho del phi by del t plus half modulus of the this is nothing but velocity, which is gradient of velocity potential, plus gy plus f of t. So this is similar to what we had seen later. It is the tag of the streamline. So this is what we have got after simplifying, or in fact this was the Euler's equation. We just substituted v as the gradient of velocity potential, and we got this, which is known as the Bernoulli's equation for unsteady or steady potential flow. So this is for unsteady or steady potential flow. Now if you want the difference between this and the previous Bernoulli's equation which we had seen, if you remember, in our previous Bernoulli's equation, if we go above, so in our previous Bernoulli's equation, we had said that it is a rotational, it could be a rotation flow, ideal flow, and a steady flow. It should satisfy these three conditions, and hence we got this equation. And also this was kind of a vector equation which you got with vectorial signs here. But now in our case, what we have got, as you can see, we have taken magnitudes and stuff. So this is kind of a scalar equation for pressure under the assumption of potential flow for steady or unsteady flow, right? So this is what we have got. And also, since we are talking about potential flow, it should be strictly irrotational. So this is the main difference which we have found out. And okay, so coming to the first point, ki why did the name potential flow come at the first place? So if you see, if you actually see that, suppose the main assumption which I am considering here is rotation, and suppose I have irrotational fields or whatever. If you have done some physics, we say that if the fields are irrotational, mostly they are conservative fields. All right. And if we are dealing with curl in any equation, curl generally signifies that the field is non conservative, and in this case you cannot actually find out a function which you can just simply take the gradient of that function to get maybe force or velocity, etc. But that is in case of non-conservative fields. But in case of conservative fields, you can actually take out the gradient of any function which you can find, and that will spit out the quantity which you want. So maybe you can think of that way. From there the idea of potential flow came in, and that's how this flow came to be known as the potential flow. So that was about the potential flow. In our next class, we'll talk about what a stream function is. So now we have talked about the gradient of the potential flow. Next, we'll deal with some cross products as well, right? So that's going to be interesting. So that's kept for the next class. Till then, stay safe and take care.